Hey, what's up, guys? This is Dr. Vivek Palipuram bringing you the next lecturette in ECPE 127 random signals. In this lecturette, I'm going to discuss joint random variables. So far, our discussion in ECPE 127 has focused on a single random variable. But in science and engineering, oftentimes we work with multiple random variables together to explain a phenomenon. So let's consider a case of the ongoing pandemic coronavirus. Let's say that we are interested in modeling time z, the time it takes for the pandemic to disappear completely. Now, this random variable z may depend on some other variables. Let's say that it depends on random variable x, the time for the vaccine to be actually made, and y, the time for the vaccine to act. So I can express z as some function of x and y. One of the simplest functions would be z is equal to x plus y, meaning that the first all of the vaccines are made and then they are administered, and then you measure the time it takes for the fever to come down, and then you can kind of model what z is going to be like, the time it takes for the pandemic to disappear completely. So that's an example of a joint random variable. So if I have a probability density functions or some probability models, let's say, that can explain the joint behavior of x and y, then I can model z. So that gives rise to this new concept in ECPE 127, which is joint random variables. Just like a single random variable assigns a number to the outcomes in the sample space, joint random variables are going to assign a set of numbers to the outcomes in the sample space, where each component of this set is going to be a number for a particular random variable. Let's consider the example of flipping a coin twice. So let's say that for some reason, I define a random variable x, which is equal to 1 when heads is there on the first flip, and it is equal to 0 if I get tails on the first flip. Let's also define this random variable y, which is equal to 1 when heads is there on the second flip, and it is equal to 0 if I get tails on the second flip. If I were to use these two definitions of random variables x and y, I can assign these sets to the outcomes in the sample space. For example, if I were to consider th, I got a tails on the very first flip, therefore x is equal to 0 here, but I got heads on the second flip, that's why y is equal to 1. And similarly, I can assign numbers or set of numbers to the other outcomes in the sample space. So your analysis has not changed a whole lot from single random variables. We are just adding one more random variable. So now, instead of assigning a particular number, we are now assigning some sort of a coordinate to these outcomes. The joint CDF, or the joint cumulative distribution function of two random variables, gives you the complete probability model for the joint random variables x and y. Just like how a single CDF gives you the probability that random variable capital X is less than or equal to small x, the joint CDF x comma y gives you the probability that x is less than or equal to small x and y is less than or equal to small y. That's the definition of joint CDF, a simple extension to single CDFs. Now, it should be noted here that we will barely or will almost never rely on cumulative distribution functions to calculate probabilities because they're quite unwieldy to use. I'll show you why exactly. So the joint CDF gives you the probability that random variable capital X is less than small x and capital Y is less than or equal to small y. Essentially, we are interested in finding the probability that random variables capital X and capital Y, they belong to this shaded region. Let's look into some theorems with respect to joint CDF. Your joint CDF is a running sum of probability values nonetheless. So it's always going to be less than or equal to 1, but greater than or equal to y. This is always true for a joint CDF. Using your joint CDF, you can get individual CDFs of random variables x and y. by setting the other random variable to infinity. For example, if I want to get the CDF of random variable x, I would set y to infinity. Essentially what I'm doing is I'm trying to evaluate what is the probability that x is equal to, or x is less than or equal to small x for y less than or equal to infinity. I'm essentially asking here, hey, what's the probability that x is less than or equal to x without regarding y, or totally disregarding y here. So that gives me the marginal CDF of random variable x. Similarly, I can get the marginal CDF for random variable y by setting x to infinity here, by disregarding x in the joint CDF. F of x at infinity comma infinity will always be equal to 1 because probability that x is less than or equal to infinity and y is less than or equal to infinity is equal to 1. F of x comma y at x comma negative infinity is equal to f of x comma y at negative infinity comma y, which is always going to be equal to 0. That is true because both x and y will always be less than, or they will always be greater than negative infinity. This theorem 5.2 is used to solve probability problems with joint random variables if you would like to use their joint CDF to solve probabilities. So let's say that I'm interested in finding the probability that x belongs to an interval x1 comma x2 and y belongs to an interval y1 comma y2. Then how can I use the CDF? This is how I'm going to apply the CDF. First, I will evaluate f of x comma y at x2 comma y2, then subtract fxy at x2 comma y1, then subtract fxy at x1 comma y2 plus fxy at x1 comma y1. So you can see here how unwieldy your joint CDF gets. So there's a good reason for you guys to start developing this hatred towards joint CDF and rely on some other probability models instead. Now let me give you the proof for this theorem. Specifically, we need to find the probability that x and y belong to this shaded region right here if we are asking for the probability that x belongs to this interval and y belongs to this interval. Now this can be proved graphically. This shaded region here gives you the probability that x is less than or equal to x2 and y is less than or equal to y2. When you subtract the probability that x is less than or equal to x2 and y is less than or equal to y1, you get this shaded region right here. So you essentially removed the bottom shaded region. Now I need to somehow eliminate this region. So I'll try to remove some more CDF values. So let's say that if I were to remove fxy at x1 comma y2, I eliminated the region that was present here, but while doing so, I eliminated this region once times too many. Because I eliminated this region one times too many, this region which corresponds to x1 comma y1, I need to add it back to the probability values. So I'll add that back and thereby I'll regain this region and find the probability that x and y, they belong to this particular shaded region. So that's the proof. Now let me give you some examples on how probability problems and other aspects are solved using the CDF. And I'm going to show you how unwieldy they actually are. Let's say that fxy, the joint CDF, is given by this massive equation right here. So you can see that why there's a good reason to hate them. They are like really awkward looking. Now let's say that I would like to get the marginal CDF of x. To get the marginal CDF of x, I need to disregard the random variable y by setting it to infinity. So I'll look into this joint CDF and see in which functions y has the scope to go to infinity. So y has the scope to go to infinity right here because this statement only depends on x is less than y, so x is less than 5, so y can go to infinity here. Y cannot go to infinity here because you are explicitly constraining y to be less than 6. Y cannot go to infinity here either because you're constraining y to be between 6 and 7. Similarly, y cannot go to infinity here, but in this part right here, y can go to infinity because y can go from 7 to infinity. And in this otherwise term as well, y can go to infinity. So when I set y to infinity, these are the only parts of the joint CDF that I can retain. And these parts will constitute the marginal CDF of x. So therefore, the marginal CDF of x is given by these guys. Similarly, what I would like for you guys to do is solve for the marginal CDF of y by setting x to infinity. Just look into this joint CDF and see in which lines x has the scope to go to infinity. All right. So I'll stop my discussion on joint CDFs right here because that's the probability model that we are never ever going to work with respect to finding probabilities. Instead, we'll be relying on joint PMFs and joint PDFs to analyze the joint random variables of discrete and continuous random variables. So first, let's discuss what a joint PMF is, what a joint probability mass function is. From your unit 2, we defined the probability mass function for a random variable x as the probability that random variable capital X takes on a very specific value, small x. For some families of discrete random variables, this PMF takes a nice equation, something like this. It's a binomial random variables PMF. This concept can be extended to multiple random variables, giving rise to joint PMFs. So joint PMF of x and y gives you the probability that x is equal to specific value small x and y is equal to specific value small y. So this is just a simple extension. All the properties of PMF, of a single PMF, also apply to joint PMF. For example, in the case of single probability mass function for single random variable, I was interested in finding the probability that x belongs to a particular set B. And I would find that by adding the PMF values for those values of x that belong to B. I can extend this to joint random variables as well. So now, to find the probability that x and y, they belong to any set B, I need to add the joint PMF for those values of x, y for those coordinates that belong to this region B. So now set B is no longer a set. It is a set, but it's better visualized as a region. So now B is actually a region. Using the joint PMF, you can get the individual probability models for random variables x and y as well. Meaning you can also get the single PMF of random variable x and random variable y. And this is how you can get it. When we extract the PMFs of x and y from a joint PMF, we call them marginal PMFs. Marginal PMFs are essentially just the PMFs. So there's no specific reason why we have to be confused here. Because we are extracting it from a joint PMF, they are called marginal PMFs. So you can just simply call them PMFs. So PMF of x is obtained by adding the joint PMF over all y for different values of x. For example, I'll add the joint PMF of x, y for x is equal to 0, and I'll perform the summation over all y. When I do that, I get the marginal PMF of x. Similarly, I can obtain the marginal PMF of y by adding the joint PMF for all x for different values of y. And I'm going to show you how you can construct joint PMFs for discrete random variables and how you can also get the marginal PMFs as well. So I'll stop this lecturette right here. This lecturette served to introduce you to the theory of joint random variables, why they are useful, and some of the probability models that are used to describe joint random variables. CDF, the joint CDF is used to describe, or it's a complete probability model for a joint random variable, but we'll never use them. Joint PMFs are a simple extension of single PMFs, which are used to almost exclusively used to find the probabilities of different events with respect to random variables x and y. So I'll stop this lecturette right here. In my next lecturette, I'm going to solve this problem 4, and I'm going to show you how the joint PMFs are applied.